Yeah. Thank you to be here also for the lecture of today. I have a bad cold. We can see, excuse me for the voice, of course. I forgot always to bring something which we can improve my voice, but anyway, somewhere I will remember that. Let me share a little bit better. I don't know if you. I hope that you hear me well. Let me check another thing. This could be a possible interesting question. Do you remember? This is not the last one. Huh? But I don't see. Yeah, clear. Do you remember this example here? The solution, I mean, the question was, I have two vectors, v1 and v2, and they have a point. Huh? The question was calculate the plane generated by these two vectors and pass it through point P1. And we did, we discussed, I think, a couple of times also with two different methods. I don't know if you remember. With two different, I don't remember well. But anyway, we discussed. Now, at the end, I received an interesting question. If I have this, let me conceive another question, which consider I will give you the plane this here, and then I ask, please demonstrate or to prove that this plane is generated by V1 and V2. And moreover, this is easy, we have seen also last time directly, does the point P belongs to the plane? That makes sense, and a possible question also in the exam. Think about 1 minute, the 2 minutes, and then we will go through together, because can help to go in depth on some aspect which we discussed last time. In any case, I try to help you with the answer. To verify that the point belongs to the plane is not so difficult. If you remember in high school, the concept of that the point satisfies the equation. This is the concept of, in my math, of belongingness. If x equal 1, y equal 1, this is the point. Because it's fixed. The point is fixed. It's not a direction. Here we have two directions. Therefore, t could be positive, could be negative, because t belongs to R. The same for k. Z x equal 1, y equal 1, z equal 1 satisfies this condition. This is the concept of belongingness, math. I don't have time to go in depth on this, why the belongingness is. Anyway, I think this is implicit in your knowledge. I can because roughly speaking, we have a condition to be satisfied by a point characterized by x, y, z. I can explain it a little bit quickly, but in this form. Think about the question. It could be an exam question. Proof that this plane is generated by the direction 1, 2, 1 and 3, 1, 1. I give you in a couple minutes, but I would like to recall what we did last time. I don't know if you remember that we discussed a lot about the vector. Please pay attention here. 1, 2, -5. I don't know if you remember this. I told you a lot about the vector. 1, the coefficient of the element x, 2, the coefficient of the or element y, and minus 5, the coefficient of element z. And we have seen, we observed, I can say we demonstrate that this vector, please pay attention, is orthogonal to the set of the plane, or the set point of the plane, or the plane, let's say. The plane is the set. If I say the set of the points of the plane is a little bit redundant, but makes nevertheless sense. If you want, I can recall this concept, because this element here states in a parallel plane to the plane 2y minus 2. I mean, this plane here is characterized by, let me say, passing through, if you put x equals 0, I mean, the plane 2y minus 5z plus x equals 0 is parallel to this plane here. Do you remember last time I told you this? How we can demonstrate this? Let me see if I find, so I can save time. I don't know if now quickly. But probably yes. So I think we did. Yeah. Let me see. I didn't find exactly the example, but I find a similar one. Let me show you what I intend, and then we will go to the to the answer. Because this could be nice to recall, to try to answer. Last time I showed you something like that. Calculate the plane orthogonal to this vector and passing through, or if you want, the point P, 1, 2, 3 is in a different example, but in order to recall the concept which can help us to answer the question of today. P belongs to this set which I want to calculate. I called here direct solution. Why that? You remember I insisted on this. I insisted because in this condition we have both, therefore the name directly, we have both, let me say, specification. 1 minus 3, 1 is orthogonal because dot, 1 minus 3, 1 dot something I will discuss here together with you equals 0. And I am including also the belongingness of P. Why that? Because x minus xp, y minus yp, z minus zp for x equal xp, y equals yp, and z equals zp satisfy this. This means this condition satisfies both specifications. The specification of P belongs to the plane, and the specification that the plane in which the point P is included is orthogonal to the set. Here is a little bit difficult to figure out, but you remember with the line, I showed you with the graph with the line last time in order to understand why this difference. Because what I am doing with these differences, I translate just the plane of the set. With the line, I told you last time very, very well. I don't know if you remember. Should I show you again? The line, in order to figure out that this is just a translation of the plane on the point P. You remember this, the idea? Yeah. You remember? Of course, could be also nice to draw here, but in 3D it's difficult to see, believe me. Therefore, in the exam, I don't ask absolutely no graph because for engineers, sometimes important to graph, as to important to figure out with the hand, but nevertheless it's difficult. Now, do you remember -1, -3, -1 is orthogonal to this, is clear. Has is orthogonal to xp, if I put here xp equals 0, yp equals 0, zp equals 0. This is the concept of the translation. If you remember in gymnasium, if you recall, x minus xp equal x apostrophe. Last time I told you, if you recall y minus yp, y apostrophe. If you recall zeta minus zp, z apostrophe, we have a translation of the system coordinates. I don't know if you remember in gymnasium a little bit. This means it's just a translation. I put my plane somewhere. Where? In the point P. Because the point P satisfied this condition here. This means the vector 1 minus 3, 1 is orthogonal to the set, but is orthogonal to all parallel sets. This means for each xp, yp, and zp. And roughly speaking, if you remember this element here, 1 minus 3, 1 remains in this, let me say, in the structure of the plane. Now, if you remember this from last time, let me come back to the question of today. The question of today was demonstrate that plane. Do you remember the plane Q?
1x, 2y, minus 5z.
Something like that. Equal 2.
Minus 2.
Minus 2. Is generated by V1, if you say me V1,
1, 2, 1.
And V2,
V1, 1.
thank you, and P belongs to it, belongs. Solution. Yeah, we can start from the last one, which is easy. I already told you before. P belong to H, it's the plane. The proof is 1 which multiply the point P. I forgot to put here is 1, 1, 1.
Yes.
Excuse me, I forgot to say. This means 1 multiply 1 plus 2 multiply 1 minus 5 multiply 1 equals minus 2. Is satisfied? Yes. I don't want to comment here. We discussed a little bit before. No? We know from Gymnasium, satisfactions, and so on. Now, think about the first question is more interesting. We have to demonstrate or the proof that V1 and V2 generated display. What do you think? Yeah. If you remember what I told you until now, that the vector 1, 2, minus 5, exactly in the order which I told you, 1, 2, minus 5, must be orthogonal to the set. I recall very quickly, but I recall the concept. This means it must be orthogonal to both. Think about how we can demonstrate it.
And we can
Do the
calculate scalar product.
yeah.
And when it's 0, the plane and the vector are orthogonal.
Yeah. Perfect. Let me write a couple of sentences. To verify, let me see. The first question, let me see quickly. No, we understood very well what is. It is enough to show that vector v equals 1, 2, minus 5 is orthogonal to v1 and to v2, but to be really precise, should be demonstrated, this is okay, no? This is not wrong, that any linear combination of V1 and V2, because generated by V1 and V2 implies, you remember in my mimic, you know, that to every linear combination, basically, also from my mimic, if you think about generated by V1 and V2, and you remember I showed you, this means not only the vectors, but the set generated by the vector. Of course, this is just a fine thing, but I would like to show you how. I mean, to show that V is orthogonal V1 and V2 is no problem. Let me complete the answer. But more in general, it is more, how possible to say, precise to show that any combination of a linear combination, I told you I forget to write, of V1 and V2 are orthogonal to V. Because any linear combination is implicit in the word generate. I don't know if you I get all points. Because if you look at the inner product between this 1 to 5 and this is clear, no? We can see. Let me check. V dot V1 1 2 minus 5 dot V1 is 1 to 1. It is 0. It is, no? 1 multiply 1 is 1. 2 multiply 2 is 4. 5 multiply minus 5 multiply 1 is minus 5. It's 0. Should I calculate for you? Yeah. So we repeat everything. Did you agree? I can do also the same V dot V2, I hope. 1, comma 2, comma minus 5 dot 3, comma 1, comma 1. I hope it's 0. Let me check. It is. Yeah, it is. Basically, this is so almost enough. But to be precise, generated, if you remember my mimic, I have to demonstrate that the set which is generated is orthogonal to this vector here, but it's not so difficult. Because as I told you, as I clarify here in this explanation, I have to consider any possible linear combination. This means how I can do. I can do in this form. Formally, V dot what? T V1, we called zone, something like that, plus K V2 must be equal 0 for each, excuse me, for each T and K. Do you remember in the slide, in the formulation of the problem, no? Formulation, when we find the solution, we characterize, I think, V1 multiplied by T, V2 multiplied by K, or vice versa, it's not relevant. Just to reflect this word generated. I insisted before last week. Now, if you're able to show this, it's directly what should be the precise answer. But anyway, also this calculation help a little bit to intuitively to understand. But really, this is the solution. It's the solution, the answer to the first question. About the belongingness of P is clear from Gennaro, satisfaction. Here a little bit more abstract, but it's clear that all points generated by V1 and V2 in the context which we discussed last week and before this are orthogonal to V. And this clarifies a little bit the meaning of generated or generation and so on. Let me do the calculation with you. This means should be 0, there must be 0. For each T and for each K means, please pay attention, independently of T and K. For each, independent. I think you already did the calculation. One, let me copy because I already forget. I already forgot here. 2 minus 5. Here we have 1 to 1 is V1. And V2 is 3, 1, 1. Huh? I hope that I copy correctly, because if I make mistakes, we don't find 0. Now, we apply the distribution. Do you remember at 2, 3 weeks ago, I told you that when we have, I mean, roughly speaking, the dot product satisfies the distribution property. This means this way to write means the vector v dot the vector t multiplied by 1 plus the vector v multiply the dot the vector k multiply v2. We have here. Just to understand what is this. T, yes, I'm stupid. What I applied here, do you remember I told you the scalar, what is the meaning, the definition of a scalar multiplying a vector? Excuse me if I repeat again the definition, but math is the definition. Because if I define another way, we have another math. Now, distribution property, I told you about that. If you don't remember, it's intuitive from Gymnasium. It's a property which can be proved. Do you remember? I told you many some weeks ago. Now, let me apply this. This means, remember, recall, in order to understand. Means this. Distribution property, if you want to write. Of distribution property of the dot product with respect sum. No, let me apply. Means one which multiply this. This means t, one which multiply this, plus 2 which multiply this, plus minus 5 which multiply this. Four, no? Excuse me, yes, 4, no? No, excuse me, in order. 9, 4. I'm so stupid. It's because I see, please correct me right now, no? Because I'm, should be nice if, this means I do here the same, 3k plus 2k minus 5k. It is 0? Yes, for each t and k. Of course, as I told you, also the calculation which we did before was almost enough. That is just formally. How that? Because this, and this, and let me say so. This, and this. I don't know if you see it. 0 for each t, 0 for each k. Therefore, I told you this really formally more precise, but the solution was already calculated when I did without this t and k. This formally because t and k characterize the concept of or reflect the word generated or generation, or let me say the set. Clear, no? Now. It's a good repetition. Believe me, math, in my opinion, is so difficult. Even though sometimes when going ahead, when we build more structures, could be a little bit more complex in the form, but very important to recall the definition, what I intend with the word generated. Now, I try to explain this. Okay, now I would like to open the lecture of today, the new lecture, the new topic of today is a little bit boring. Therefore, I try to speed up a little bit because I have to recall the concept of the matrices, or the matrix. I have to recall the concept of the determinant, probably you know from Gymnasium, I don't know from Gymnasium, from Math 1 or the Math 2. And then after this this part, we can consider more interesting mathematical problems. Also, in economy, we will see that could be important. Nevertheless, recall some concept. Okay, you can find the lecture number 5 in my study. I will try to now let me share. Looks like something like that. We can see December 2020 in order to show you that this is a lecture. I think we have some part which should be corrected, but they are just formal correction. I didn't have time to do. Oh, I don't remember. Let me see. But in any way, it's just background. Not is new. Let me start with this slide here. Quickly, as I told you, I skipped the definition of a matrix. What is a matrix? The matrix is in the table of values. The table of values. But as in the table of values, has many properties, a lot. Here we will see some of them very quickly, and then using exercises, we will recall properties and characteristics. In this course, I don't know if I have time at the end a little bit to tell you about the differential equations. Probably you heard about differential equations. I have some courses here in complementary studies in which we will use matrix in differential equations. The matrices are one of in math, in engineers, but in math, the concept of the matrix is one of the most important concepts because this table of value summarizes or compress extremely important characteristics of dynamical systems or static systems or set of data. Anyway, I don't want to now to do a list where we can apply this, but believe me, almost everywhere. Let me go ahead. I have a table or tables of values. We can see here 2 tables. If you want matrix, very quickly. Matrix A and matrix B, which we can see very quickly, really, which we have the matrix A, which is characterized by 2 rows and 5 columns. And each element is, let me say, characterized by coordinates. That is easy to intuitive. I think I don't need to spend energy here. The same I can say for the table B, we can see here, which is the matrix 4 row, 3 columns. Very often we say that the matrix A is in the matrix 2 times 4, and the matrix B is in the matrix 4 times 3, related to the number of row and column. we can see, I don't know if you have mistakes here. Let me see, because I remember there is a mistake. The product between two matrices are characterized by we can see here the product, which is characterized basically by what? By the dot product we know, between row and column. Here I put a couple example. We can see the first example here, the second here, just two examples in order to flesh out the definition of the product. But if you remember the definition of the dot, we don't need, I don't need to clarify much, because C11 again is characterized by the dot product between, C11 means the dot product between the first row of matrix A and the first column of matrix B. We say product row column in accordance with this definition. It's a definition, of course. If I define a different way, I have a different solution. But of course, the sense of this definition is, with this definition, we can explain many things. We can explain many things. Now we can see C11 is A11 multiply B11, A12 multiply B21, A13 multiply B31. If you remember what I told you about the definition, you can recognize the product of the corresponding, the sum of the product of the corresponding element, but first row, first column in sense of dot. And here, another example in order to understand, C22, this element here, means the second, look at here, the second row of the matrix A multiply the second column of the matrix B. Check. I don't know if I have some errors. I hope no. But anyway, it's clear what I want to intend. It could be that with LaTeX I made some mistakes, but it's clear what I intend. Very important to notice, this product is defined between matrices which have, if I remember, if you remember, I told you the product is the dot product characterized by row, characterized row by column. We say row by column. This means the number, please pay attention, the number of column of the matrix A must be equal the number of row of the matrix B. You don't have to keep in mind this. You look at the calculation is quite clear. This vector multiply this vector. It is possible. I don't know if you remember the dot product. If the two vectors have the same components. Again, this vector is in the row vector. This vector is in the column vector. As I told you, the number of this component must be equal to the number of this component. This means the number of column of the first matrix, let me say, and the number of row of the B matrix must be the same. Now, very quickly, I can define, could be nice if you have time to show you some properties of this transposed in dynamical systems, but I don't know if this semester we have time. Anyway, we can define also a transposed matrix, which basically change. Now we have the definition row with column. We can see here A11, A12, A13. The transposed of this matrix changes the row with the column. We can see A11, A12, A13 now is in the column. Instead of the first row is the first column, and so on. I don't know if you remember from math. You can see here, this is second row becomes, once it's transposed, the second column. Let me quickly tell you about these properties. In particular, we can see, just flesh out, we can see that the transposition is a property which is not distributive. In some books, we say we find anti-distributive, because we can see that I distribute this operator which we define here. The transposition is, I invert. It's not invert. Invert is a little bit strange. I change, interchange, how possible to say? Row with column. the product between A and B transpose equals B transpose dot A transpose. I didn't put dot because when you have matrices, it's always a dot. The product is in a dot form, but in the definition, in the form which I explained here or defined here, we can see that it's not distributive because I have to, let me say, change the order. We can demonstrate that the left, if I consider a generic matrix A and a generic matrix B, equals the right in this form. This means this is the property. I can also demonstrate that if I have three products, I can write in this form here. I can also proceed ahead. We can see that if the product consists of 4 elements, I have somehow considering the order in this sense here. The last become the first become the last, and in this context here. If the number is odd, here we have an even number of product. We have one which remains, because it's something like symmetric structure. Anyway, we can demonstrate that the left equal right extremely easy but boring. Look at this. Probably you remember from gymnasium this. Let me show you the inverse of a matrix. In inverse of the matrix, we can say that B is an inverse of the matrix A. If, please remember in definition, if means if and not if. B multiply B, or that scalar B, or that dot, B dot A equal identity matrix. I is an identity matrix, is in a matrix which we can see here in the last part of the slide, which is characterized by all zeros except for, and the diagonal when we have 1. This is the identity matrix. Please pay attention here. I told you that the inversion is defined, at least until now, or in this definition, just for squared matrices. A must be in a squared matrix. This means also A in a squared matrix, because otherwise the product is not possible. But of course, in more advanced application, we can somehow define the inversion of square matrices. Please remember this. We will see later that B multiply or A is not equal A multiply B, but A is equal in case A is B is the inverse of A. But we can demonstrate that if B is the inverse of A is the inverse of B. I think I have in the next slide. Anyway, I think this you know from other courses, that therefore I was not so, I sketch here some knowledge and important probably in order to understand a little bit better. This example. I have the matrix A, and if I ask, please calculate the matrix B, which is the inverse of A. How we can do? Very important. I parameterize the matrix B using parameters A, B, C, D. I know that A must be squared. It is. Otherwise, in accordance with the definition which I told you before, we cannot calculate. If the definition is different, of course, we can do some different calculation. Now, I parameterize the matrix B by A, B, C, D in this form here. And then I apply the definition. The definition is B multiply A equals 1, 0, 0, 1. Recall the definition. B, let me say multiply A equal identity matrix. Look at the definition. Clear. Applying the definition, I can calculate A, B, C, D. Row multiply column. A multiply 1 plus B multiply 0 equal 1. I put directly A equal 1. I don't know if it's visible for you what I did. Row multiply column. A multiply B the dot product between row and column. Again, it's not the definition. Apply the definition, we will find the solution if the solution exists. Otherwise, if it does not exist, we have to discuss why it does not exist. But in this case, we will see that it will exist. A multiply 1 plus B multiply 0 equal 1 means A equal 1. Then, second element. This row multiplies this column. This means 2 multiply A plus B, because 2A multiply 2, to be precise, plus B multiply 1 must be equal 0. We can see this expression, this condition. Then I have the second row to be considered. C multiply 1 plus D multiply 0 equals 0. This means C equals 0. Is this too difficult to do? No, I don't think so. What should I do on the lateral camera?
Yeah.
It's better, no?
Yeah.
Okay. We are here that everybody should understand. As I told you, not for everybody is something which you already. When you are tired, we can take a little bit of rest. No? We do this calculation, then we take 10 minutes. Yeah? Okay. Calculate, given, let me say, given matrix A equals, I already forgot, 1, 2, 0, 1. Yeah? Calculate the inverse of it solution. Let be the inverse matrix of A. And let B equals A, B, C, and D. As I told you, B must be calculated. In order to be calculated, I image that exists for parameters structured in a squared matrix. Matrix in the table, no? Matrix equals table. No? We have a table. Such that, let me write so, no? Or let me write for you if you want. B multiply A equal identity matrix. This means, this is in accordance to the definition, exactly what I told you in the slide. A, B, C, D, we multiply 1, 2, 0, 1 equals the identity matrix 1, 0, 0, 1. Clear, no? Which means what about this element here? Let me probably I'm writing too fast. Because I know that not for everybody is clear what I intend. Let me do really each. I copy again what I already wrote before, so I don't need to change the sheet. Again, I copied, so we have it here. Look, do you remember the product between these two matrices is this row multiply this column to generate this element here. This means A multiply 1 plus B multiply 0. A, did you agree? A multiply 1 plus B multiply 0 is this element, the element 1, 1. What about this element here? The same row multiply the second column. Do you remember I told you before, this element here is the element 1, 2, first row, second column, which is generated in accordance with the definition of the product between the first row and the second column. This means A multiply 2 plus B multiply 1. Did you agree? Now I do the same for the second column row, I would like to say. This means this row multiply this column. Why that? Because this element here is the element 2, 1, second. 2 means second row of first column. This means I multiply the second row by the first column. It's everything corresponding to the index which I indicated probably a little bit too fast but at the beginning. C multiply 1 plus D multiply 0 is C. What about here? Row multiply column. The element 2 times 2 is obtained by the product, by the second row multiply the second column. Here we have the element 2 times 2, second column, second row. We can say very briefly. C multiply 2 means 2 times C plus D. Now, in order to calculate A, B, C, D, I have enough conditions, of course, because when two matrices are equal, I didn't tell you the equality of two matrices, but it's intuitive to understand. If you remember the equality between two vectors, vectors is also in a table of elements. When all corresponding elements are equal. Remember this? Here is the same, even though I didn't tell you as a possible definition because I assumed that you remember, or basically it's intuitive. All corresponding elements must be equal. This means let me intuitively A must be equal 1, C must be equal 0, 2A plus B must be equal 0, and 2C plus D must be equal 1. Everything together, because it's the table which is characterized of the two tables must be equal. Everything must be satisfied together. From the first one, let me sketch. Did you agree? Considering here, we have a D equal 1. At the end, we have A equal 1, semicolon. B equals minus 2, semicolon. C equals 0, semicolon. D equal 1. I hope no mistakes. This means the matrix B, which was characterized by A, B, C, D, is 1 minus 2, 0, 1. Try to do at home that B multiply A is equal identity matrix. Let me tell you one thing, and then we will stop a little bit. We can see here 1 minus 2, 0, 1. But we can also say that if B is the inverse of A, I didn't show you but probably we have here. A is the inverse of B. We can see from here. It's a little bit quick. No? We have the calculations. We have seen something better. B is the inverse of A. But we can also demonstrate that in case one of both matrices, and this is both, at the inverse of the other one, we have this B multiply A is equal multiply B, because in this case it's identity matrix. It's really I, and I equal I is in a, let me see, identity. I mean, B multiply A equals A multiply B works just if we are in the presence of the inversion of matrix. In general, is not valid. In general, B multiply A is not equal A multiply B. I don't know if you remember, but we can demonstrate, consider the generical element of A, generical element of B. I mean, generical matrix A, generical matrix B. But in case we have the inversion, we can say that A multiply B equal A, B multiply A, excuse me, equals A multiply B. But in general, not. We can see from here why. No? Because the reason is if B is the inversion of A is the inversion of B. We can demonstrate also, no? That left equal right. And therefore, we can demonstrate that if B is the inversion of A is the inversion of B. Okay, I think we can take a rest a little bit, and then we will start quickly with this definition of orthogonal. I don't know if in this course we will be able to apply, but it nevertheless could be that if I'm able to tell you about differential equation, I'm not sure about that. And then the last part is dedicated, a little bit boring, dedicated to the determinant. And yeah, we have some properties of this important. And nevertheless, today I will tell you about eigenvalues, eigenvectors with an exam exercise. Okay, I think we can stop 10 minutes, maximum 50 minutes, and then we come back here, restarting with this definition. Let me stop recording. I think it's okay, no? I stopped. Oh, it's what I forgot. It's okay, no? So, because fortsetzen, it stopped, no? Okay.
Nee, das ist nicht neu für mich. Also, das haben wir nicht gemacht in der Schule. Bei der Uni auch.
Ja, deswegen, wir sind hier etwas auch Neues vielleicht. Ja, sonst, okay. Abend, ich fühle immer schlimmer. Ich fühle mich schlecht vor, ganz früh, wenn ich aufstehe. Und abends macht ja Sinn vielleicht. Ja. Der Körper am Anfang sollte starten und dann, wenn er müde. Nein, ist nicht so dramatisch, ne? Aber wäre besser, wenn ich hätte. Ne? Ja.
Jetzt gehen wir. Ich meine, das steht jetzt. Ja, das wäre einfach noch 3 Minuten aufgehört. Ja, von Anschluss angeguckt. Wie hast du das gerade? Also, wie weit bin ich vorbereitet? Wenn es ein Framework, Use Cases haben, was mit aber nicht so wie das nicht durch oder die Fragen. Ja, weil die Frage ist zuerst ist. Weil die meinen, ja, es hat irgendwie als Schule, das ist erst auf der Kommen. Aber das ist eigentlich auch nicht. Das ist nicht. Du willst reingehen, also wir fordern das die Isa hatte eben gerade irgendwas passiert. Ja. Habt ihr dann das zusammen gemacht? Das heißt, these were the frameworks for our distributed information. Was hat man gesagt? Wann war der da? 12. Vielleicht checken wir es ja. Die checken wir es. Und hast du auch dieses bei Organization, Integration, Differentiation, ja, ja. Das steht dann nicht mal. Das macht. Ja. Aber das sollte ein bisschen. Ja, das war ja. Yes. Yes. Tools, so we all want to be that's a good tools making wrong.
Noch ein paar Minuten, weil abends sind ja noch schlimmer bei mir. Ne?
Ja,
die Stimme kann man merken, ein bisschen komisch, oder?
Bisschen anders, ja.
Ich meine, am Anfang war besser. Heute, als ihr heute angefangen habt.
Ja, das geht. Also.
Ungefähr gleich. Okay. Aber interessant, ich habe kein Fieber, sonst hätte ich mir, ne, weil ich ja auch gefährdet von der anderen. Aber warum diese Durcheinander? Was zu tun mit dem, normalerweise ist die Fieber, das macht Durcheinander.
Ja,
Oder,
Erkältung ist ja allgemein, schlägt ja auch das Kreislauf, deswegen.
auch ja, zu tun mit dem Wettlauf. Ne?
Ja.
Aber im Moment keine besondere dumme Sache erzählt. Ne? Viele auch nicht so viele. Ne?
Steht ja auch in Strong Deutschland, das ist halt auch wirklich so.
Ja.
Scheinbar.
Und die, wie viele Übungen sind da? Welche? Ja. Vielleicht. Ansonsten. Ja, das Wichtigste. Es gab auch noch dieses Tutorial, aber auch noch was bei Process und dann das was ich echt nicht so richtig verstehe, ist dieses wie verstehst du den Sinn, wie du sagst, wie Capabilities?
Ja.
Ich verstehe noch nicht, was das im Kontext ist.
Ja. Ich finde das gerne übrigens. Dann äußerst du die Erwägung der wobei erstmal
Weil ich jetzt das ging und dann ist ich habe das mir nochmal später abhaken. Das Framework. Das ging ja auch irgendwie diese, das also Background, ich will nur ja.
aber
Noch 10 Minuten, ich mache einen anderen Anruf. Ne?
ja,
So, dann geht weiter. Das war hilft ein bisschen eher. Ne?
vorher sagen können, die einen von mir aber dann lernen kann. Kernkompetenz kommen. Diese Modelle sind da auch kennen.
Ja. Obwohl ich schon angefangen zu lernen. Dann würde ich so lieber versuchen jetzt, weil ich glaube, wenn du dich darauf vorbereitest, dann findest du eigentlich durch. Also, das glaube ich passiert.
Vor allem auch wenn ich extra ich meine,
Müssen sie eh nächstes Jahr nochmal schreiben, so müssen sie ganz sicher nächstes Jahr noch schreiben. Das ist irgendwie ein bisschen mutig. Da haben wir ihnen eine Verwurzelung. Ja, wie ist noch? Aber der einzige, der sie da hat. Nur beim Feierabend
Ja, vielleicht noch irgendwie.
werde ich nicht mehr.
Von morgen die Studienbereich.
Wenn du gehen morgen. Willst du das mit der ISO haben? Du hast ja die ja, das stimmt. Danach wollen wir nicht mein ganzes Wochenende schon super planen und dann ist der Scheiße, wann wird. Ja. Nicht bisschen. Ja, schön, ich war Monat. Ach, ja, selbst in uns halt.
Sprachen, Wörter letzten haben ja auch online, also 1500 Wörter, deswegen denke ich mal, in der Schule Anschluss gemacht werden.
Ich denke mal, wenn du dann eine Stunde lang sitzt und nicht weißt, was du schreibst, dann kann ich sagen, dass es das Weg ist.
Man muss ja erstmal lesen, ja, stark. Bevor wir sprechen. Ja, das Leben ist irgendwie, ja. Den Fall anfangen. Hast du noch dreiviertel Stunden für den ersten Teil oder den Fußball, dann haben wir das nur Plättchen. Wenn wir auch bei das Weihnachtsfeld.
Ja, denkst du. Was du in okay, ich dachte, du die ganze Zeit. Ja, oder sagen wir, wie es wird. Ja, natürlich, das ist natürlich.
Nach Kopulär und auch Pension längst komplett. Weil ich jetzt viel ja, weil man natürlich auch alles wie uns und
dann alles Leistung, also viel.
Ja, und jetzt 30 Seiten Text.
So, das kriegen wir
Auch noch. Anfangen, soll man zum Anstelle stellen, weil wir sollen nicht tun. Nur letztes Mal habe ich gemerkt, dass jemand anderen kennt.
Oh, ja, wir haben ein paar Minuten. Noch.
Ach so. Ja, sowieso ein paar Minuten. Ja, das geht. Ist wieder besser? Ein bisschen. Wow, okay. Ja. Vielleicht verschiedene Leuten kommen. Sonst können wir auch wieder bauen, aber das ist nicht die das leider die Belege fand ich gegeben habe und ich habe es probiert, eine bessere Stadtbecken, genau, und hatte zu okay. So weiter mit diese ja, ist bekannt. Jetzt machen wir also gesagt. Das Bus, die Welt. Also, weil die meisten sind zu Hause bei wahrscheinlich auch, die Effekte sind nur bei dir.
Und wir hatten heute einen Ausfall, wir hatten heute quasi keine Online, keine vor Ort
Okay.
Vorlesung, deswegen sind halt viele in Hamburg oder so.
Ja, es geht einfach voran. Ich muss gerade neue Beobachter zu bauen. Okay, Beispiel ist immer abhängig. Das war jetzt ein bisschen ja, so wie man sich das zu auf unser System. Okay, ja,
Ja, ich warte, ist noch es ist jetzt, dass wir
irgendwas, ja, aber es ist irgendwie auch schwierig, das alles genau zu interpretieren.
Wirklich?
Ja, ja.
Wenn wir was da.
Ich habe zwar gesehen, die haben auch vielleicht mal Track und so, aber das kommt über die Zeit. Ja, auch schon. Ich glaube, große Chance. Ja, von ja. Cool. Aber auch das ein bisschen gut. Ja, ich
war auch nicht halt wirklich
aber unsere Lösung ist, was man lieben hat. Das ist also gut, der nochmal das geeinigt, das heißt, aber genau nicht immer reproduzieren, aber gut mal
und nächste Woche
sagen, das
von
gibt es
der
eine A, W und eine Nummer drauf und gut. Guck mal, es ist ja noch bis zum 5. Dezember viele reichen jetzt zum Ende. Weil ja.
Ja, das stimmt. Aber wenn du es
Es war sehr schönes Wetter. Es war über 25 Grad. Das sehr angenehm. Viele Autos und
es ist ein schönes Hotel eigentlich.
wir haben es ja auch ganz schön. Aber Hotel war okay. Also ich habe bei Booking bekommen, das sah schon deutlich besser aus. Ja, also, aber es ist ja auch nicht gekostet. Nein, ich bin immer noch da.
Das ist ja.
Gegen mit jetzt doch alle Gewissheit, das
Bisher
und gut bekommen. Die Leute waren da. Sondern am Samstag war es so schön.
ja.
Ich war auch schön, dass ich selber.
Und wenn man die Stelle.
Das Problem ist, noch einfach wäre. Ich sage mal, das auch dann noch.
Ja.
Das Fokus wollten dann auch andere sonst. Ja, aber ich frage mal, ich muss ja, ich habe schon auch nicht. Für die Position. Und dann sage ich auch, also man muss auch ein bisschen entspannen.
Ich glaube, ich mache ja auch
Beschäftige aus. Diese Nutzen immer sind so ja, das sind ja auch die Wochenende. Aber Kolumninspiration auch, aber ich würde etwas auf dem Kurs auch
aber es hat auch die Schule ist so nicht unterhalb von
ist die Frage.
Es geht in der Tiefe.
Ja, auch schon erzählt.
Dann bedeutet, du musst den Zug jetzt wahrscheinlich nutzen.
Ein Zug hier.
Ja, Bewegung, Konzentration, dann diese Psychologie ist auch so. Konzentration, ja, wenn er alle ja durchpasst, aber wenn die Dinge, weil dachte,
Genau.
Observation, so, ja,
Du hast nicht falsch, sondern
ja, wir schon eine potenzielle Unbegabte. Das ist die Vorbereitung, das auf die gute Frage ist, das Pro,
Ja, vorher auch schon überlegt, Bachelor würde ich miteinander fahren, weil deswegen hat das irgendwann schon natürlich jetzt noch nur für alle Zeit und Bachelor
ausgerichtet, nicht beim letzten
mir was.
und auch ja schon wie meinst du, weil ich ja aus ja, da käme ja noch aufgebaut
Das meine ich, sieht man, die Voraussetzungen, aber muss man übersehen. Weil das erste, wie die Stimmung, aber so ist das Film wahrscheinlich, ja, hoch. Aber dann das
Management Qualities.
zwischen beiden, was jetzt eine der macht, ja,
Also ich meine, die Frage ist, was auch endlich wer meint was.
Jetzt ist wieder Entwicklung. Das wir nicht jetzt mit.
Das ist kurzfristig vor allem
So,
so die letzten 2 Wochen nach dem Umstellen wieder.
ja, und das okay.
Ja, München ist
Was wir kannst du auch
ja, also ich fand es, aber ich habe es nicht so.
Nicht.
Also mich ist
Eine
das ist so, das ist so, aber so partieren.
Das ist so, ich sage, das Kunst auch a posteriori. Ist nicht
Sowieso Beine, so.
alles schön geschehen, alles fein. Nur auch formell im Szenario und Wahrheit.
Aber jetzt bin ich echt, obwohl Leute
das wäre ja sehr ärgerlich.
Wenn nicht, vielleicht so ist es. Aber so wird es das geht halt. Das ist alles. Nee, weil
Ja, wenn man dann direkt mit
oder jetzt wird diese Show gesagt.
so lustig als Plätze. Ich weiß nicht, ob ich das dann denke ich, sage Mensch, immer wie schlecht. Aber ich meine,
Ach so, inoffiziell.
Nee, so offiziell, weil offiziell auch das nicht jetzt.
Offiziell keine Regelung.
Die Farbe bekannt wie das geht. Ja, jetzt ist simuliert, weil der Kunde nicht mehr danach wollte die Scheibe.
Ja, so einfach. Es gibt auch das heute. Meine Vorschläge fahren. Aber auch was in der
Das heißt, ich bin noch sehr glücklich. Es geht was heißt, die Blumen von uns haben. Sie meinen,
Ja, ja, ist auch richtig.
was wäre das?
Ja, in der Sinne, da wenn
Ich meine, klar, auch wenn die das irgendwie so.
ich meine, alles gut, ich weiß es auch. Weiß nicht, aber ich bin zur Schule heißen. Aber ich hoffe, dass wir kommen. Aber falls danach nicht steht, ich hoffe, dass alle die Möglichkeit über das Geld einbringen, dass du die sagen. Oder wenn es ist, eine wichtige Zeit.
Also noch gerne noch mal anrufen.
Ja, oder die dürfen ja oder eben eine. Ja, also wir nicht vermissen. Ciao, ciao, Jens. Danke für deinen Besuch. Ne?
Okay, okay, all together. Excuse me. Now we will restart. Now where I put. Did you see my glasses? Over here, no. Ah, here. It happens to me that sometimes I have it here. I don't realize. It is no for you also. No. Für euch ist immer bekannt, dass die Brille sind dabei. Ab und zu mal, wenn jemand ein bisschen durcheinander, wie heute, so, wie immer. Ich merke nicht, ob die das haben. Ist normal oder auch das bis, wo ich meine Brille habe dabei? Weil wir gewohnt an diese Situation, ne? Das Gehirn gewohnt. Ja, interessant. Okay, let me restart recording. Yeah, look at this. Very quickly, this definition, even though at this moment I will not use much, but we will see if at the end of the semester I can show you some aspects related to the dynamical systems and so on. We can see directly, if you read this definition, this is a little bit different, the concept, with respect to the orthogonality in terms of vectors. You remember that the orthogonality in terms of vectors was characterized by the product is the product equals 0. In this sense, it's not exactly the same, the concept, because we can see that A transposed equals A inverse. No? Basically, the transposed matrix equals the inverse. In this sense, we say that A is orthogonal. It's an orthogonal matrix. We have to nevertheless clarify the meaning, because when we are speaking about vector, we say that two vectors are orthogonal. Here, the concept is a little bit different. It's a little bit different because we don't have two matrices which are orthogonal. It's difficult, this concept, to figure out. We say when a matrix is orthogonal. The meaning of this, I don't know if we will do in the sense of the dynamical system. I don't know if we are able to do these exercises using differential equation in order to understand a little bit the meaning of this, let me say, definition. Just remark from the definition, it follows that A transposed dot A equals identity matrix. I would like to characterize this orthogonality more than this remark than the direct definition, which we can see the remark came from the definition. Why that? Because if you multiply this equality on the right, please pay attention. Now I'm using a concept which I already explained, but indirectly. Multiplication on the right, multiplication on the left. You remember I told you before that A dot B in general is not equal B dot A. This means multiply on the right and multiply on the left is not the same. I mean, in the scalar, if I do A multiply B equals B multiply A, 2 multiply 3 equals 3 multiply 2. When you have a table of values, this is not valid. I told you quickly before, because probably you already knew it. But in this specific case, multiply on the left and multiply on the right is the same, because we are speaking about inverse matrix. You remember I told you also before, A multiply B equal B multiply A, just in case inverse matrix. Anyway, the orthogonality is mostly characterized by this product here. And the matrix is orthogonal. A matrix, not two matrices are orthogonal. This is a little bit difficult to be defined, but we can intuitively understand the meaning. Look at this. This means if you look at this means that the product between the not homologous element are zero. I mean, if you remember the identity matrix is the matrix characterized by all zeros except on the diagonal. This means this product here at all zeros in the crossing elements, or the crossing products, and one in the homologous element. Basically, let me show you what I intend. A transposed multiply A is orthogonal if we have 1, 1, 1 as a result, 0, 0, 0, let me say 0, 0, 0. This means somehow the component which is not, let me say, diagonal, the product of these elements are zero. This means recall somehow the concept of the orthogonality. The meaning or the application should be possible to see, or it is possible to see in, for instance, dynamical system and so on. But somehow now, if you think about as the identity matrix, if the identity matrix is characterized by all zero except for the diagonal, recalled somehow this product between vectors, no? Because the product between two matrices, the product row multiply vectors. But the matrix is orthogonal if A transposed multiply A is an identity matrix. We cannot say more about that. We cannot say more because, of course, when I multiply the element by itself, cannot be 0, but all the rest is 0. Because the diagonal element of A and A transpose are the same. I don't know if we can understand this. This means now we can see that reflects somehow the content, the idea of the orthogonality. But is defined for a matrix, no? Just for, not for two matrices. Of course, we can define for two matrices, matrix A and matrix B. For instance, when A multiply B equals 0, this means the row of a matrix are orthogonal to the column of the other one, because the row multiply column. No, but at this moment, let me go ahead with this. And then we will see, it could be that also here we can see some possible property of an orthogonal matrix. But itself is a, let me say, reflexive property. No? Definition of determinant. Oh, if you look at this equation here, it's extremely difficult to remember. But let me do using the remark some considerations, and then I would like to start with an example or two examples. I think before doing an example here, we have a boring situation here. Oh, okay. I would like to very quickly tell you about the properties. You don't have to learn for the examination, but it could be that can help some of them. Let me do some consideration. At this moment, try to forget the definition, because the definition is quite cryptic. Huh? Let me nevertheless say that A by J is called a minor IJ. What is a minor? Minor, Deutsch wäre minor. No? Klein. Ubi major, minor cessat, from Latin, do you know? Where is the boss? The rest, let me say, should in silence bleiben, or remain, something like that. But not here, no? Yeah, doesn't exist the boss. Yeah, minor is basically, it's written here. Minor IJ. No? We can see that the minor is in a matrix. First of all, it's in a matrix. We can see here. Is characterized by IJ, is the matrix, excluding the I row and J column. Nevertheless, does not clarify the definition. I don't know if you have seen the definition. Probably you didn't see this definition before. Okay, at this moment, don't care about the definition, but is related to it's a minor. It's a little bit still not clear what is it. I would like to add that it's defined here just for a square matrix. We can see this we can understand what it is, just on a square matrix. I would like to say it's not written here, but we can see from not explicit written here, but it's clear from this sum, which is in a scalar. This means it's an operator which associates a scalar to a matrix. I have a matrix 1, 2, 3, 4, and I will associate, in accordance with the definition, a value in scalar. If the values of the elements of the matrix are real, the determinant is real. Let me, before doing some exercises, let me tell you very quickly about this, these properties. Look at the first one. Determinant of A equals determinant of A transposed. Interesting. We can demonstrate, taking into consideration the general matrix A, that the left part equals the right part, applying the definition. We will see later, not exactly related to the property 1, how we can apply this definition intuitively. The computer, MATLAB, does the calculation in microseconds. Therefore, I don't insist on this. But let me see the property. Nevertheless, this could be interesting in some application. Determinant of A equals determinant of A transposed. Very important this. If A has row or plural rows or columns plural of zeros, is enough one row or column, then the determinant of A equals 0. Also, this is easy to demonstrate applying the definition. Why that? Because this element here, I will tell you with an example. In order to demonstrate the property, I have to consider the matrix A, n row and n columns. Square matrix, again, I don't do. If A has 2 identical rows of columns, then the determinant of A equals 0. Yeah, this also can be demonstrated in general, but this is, I would like to comment this. Somehow, this determinant, assuming that we are able to demonstrate, this determinant somehow indicates if row or column are dependent or independent. Because if you have 2 identical row or columns, as a set, if you consider this table of values and a set of row or in a set of column, in the set, you remember, the set we characterize each set of vectors, because row is vectors, column is vectors. And the table, matrices, could be seen as in a set of row vectors, or and a set of column vector. I can see as you want, I can define as I want. Please pay attention. In matter, we can do whatever we want, believe me. Very important that we don't contradict. This means it could be an interesting, assuming that I am able to demonstrate. This means can be an indicator if the set is depending or not. Somehow could be also in a measure of the dependence or independence. About the measure, I didn't tell you until now. Do you remember? Until now, we have seen some exam exercise in which please determine or calculate or say to me if the set of vectors, I didn't specify of row vector or column vector because I didn't tell you about the matrices, are dependent or not. But in this sense, could be so interesting to introduce in a possible measurements. If it's almost 0, we will do some exercise. This means that the vectors, row or column, we will discuss a little bit more in depth. Probably is almost depending. Because if we have a set of vectors in which we have 2 vectors which are the same, I don't know if I exactly did this example, but it's intuitive, understandable in accordance with what I told you until now. The set is dependent. Try to imagine. Now, the property number 4, we already discussed. If they are linear depending, again, the determinant is 0. We can demonstrate also this. We can demonstrate. This means could be interesting also the determinant and the possible measurement of the level of a set of vectors. Of course, to build the determinant, the dimension in which the vectors are defined must be the same, the number of the vector. Otherwise, I cannot structure this problem in terms of matrices. I cannot build the determinant. I can do some exercises, easy to show you, time to explain. The demonstration of this is boring because you have again to take a general matrix and then applying the definition. So But now we can intuitively understand that this possible definition try to, not only, try to build some interconnection between the vectors, row column vectors. Of course, is still complex, but the definition, the mathematician which defined this form here, looked at this. We need a structure, we need an indicator, which can tell us about some properties of this structure vector, row vector, column vector. This is always the meaning of a possible definition. Again, we can define whatever we want, whatever you want. But of course, if with the definition of some object, we can work or we can explain something, we are happy. Otherwise, it's there as a possible definition, but probably we cannot use. Nevertheless, the definition holds, the definition nevertheless is valid, even though we cannot use as a possible definition. Okay. 4, I discussed a little bit. Yeah, these also can be easily understood. I will do an example. Basically, if I change the order of 2 rows or 2 columns, we have this property here. We change the sign. If you change twice, in this case, I maintain the sign. If the column is multiplied or row is multiplied by a scalar, determinant of A equals K multiplied determinant of B. We can understand very well because it's the sum of a product. This means I can put in evidence. Just figure out the meaning of the property number 6. Of course, if I do the formal definition or the formal proof, is quite boring because you remember properties must be demonstrated. But believe me, let me conclude with this last property. Very interesting. Adding rows, columns, each other. I add 2 rows and 2 columns. Then determinant of A equals determinant of B. Please pay attention. A is without adding. B is after adding. As here, I didn't clarify, but it's intuitive. No? A is before interchanging, and B is after the interchanging. If I interchange twice, we have a determinant of A equals determinant of B, because we have changed 2 times. Here reflects somehow what I told you about the linear depending and linear independent. Does not change because somehow is in a measurement of this set, which is in a closed set. Number of row, number of column, depending or not. This means if I add, I remain in the same subspace. Do you remember? Also today we have seen 2 vectors generate in the set. This means every point in the set can be seen as a combination of this. This means this indicator does not change. Just a feeling. Of course, the demonstration a little bit says something more, but not much more. Very important to intuitively to understand a little bit where this comes from, or why so perverts. Because nevertheless, it's a strong indicator. Basically, we have a very complex set of row and set of column. You can see in both. Wait. But then we can associate a value, which says a lot. Just is the feeling. Don't learn about. We will do some exercise. A few minutes. Look at the property number 8. The property number 8 is interesting because somehow states the distribution of the determinant operator with respect to the product between 2 matrices. And this is also due to the definition of the sum, to the sum a little bit. Determinant of A dot B equals determinant of A multiplied determinant of B. That's again an interesting property because of the sum, if you think about. distribution of this operator, if you want. Now we can see that if A is invertible means if exists A up to -1. About that, I told you very quickly before when I told you if exists, it could be does not exist. At this moment, I didn't tell you any example, but if you remember in high school, today I did an exercise in which I calculate B as an inverse of A. But the solution came from an algebraic system with 4 equations and 4 parameters, A, B, C, D. If you remember in high school, now we will see together, so we have cases in which the solution is like this. I don't know if you remember this in high school. No? If you have two lines, for instance, they are parallel. The problem is find where these two lines, in general, find the point which these two lines meet. If these two lines are parallel, they don't meet. There's now a solution. Oh, I have an infinite, but we don't go to the infinite. Not yet. Yeah, if it's invertible, then the determinant is not 0. It's very interesting, this. Very interesting. Because somehow states that we have a connection between the invertibility, the determinant, of course, and the dependence or independence you can read in both, no? Of the vector. Why that? Because if you look at the 10, if the determinant is not 0, then it's invertible. This means here 9 and 10 can be considered both together, something like if and only if. Yeah? If it's not 0, this is invertible. If it's invertible, then it's not 0. But we have a scene here. Look at the property number 4. This means if it's not 0, they are independent. Very interesting to verify also if a set of rows is dependent or not. Interesting also this one, if A is invertible, then A multiply x equals 0 has only 0 solutions. This we have seen in some exercises, but reflects nevertheless the dependence or independence in the sense we have the independence already discussed here, and this means that the combination, what is A multiply x equals 0, can be seen as a system, but can be seen how to verify, which is the same, now to verify if the vector, row vector or column vector are dependent or not. What we did in high school can be seen also as vector dependent or not. The property number 2 is basically the property number 11, excuse me, the property number 12 is the property number 11 in the other direction. If with only 0, then the determinant is not 0. Because if the determinant is not 0, it's invertible. This means this operator can say a lot of things about the dependence, independence, and so on. You remember in high school, we have seen this. A multiply x as an homogeneous part of the linear system. Okay, let me do something more interesting. But we will see that this property intuitively understandable. Let me show you how we can now manage this difficult definition. It is not difficult. It's easy to do the calculation instead of explain what is. I don't insist on this much because we will apply during the semester. In any case, I will tell you, I will put in the data sheet the definition, but you will realize that is intuitive to be applied. Also because in the exercise we will do together, I will not consider determinant for matrices larger than 3 times 3. Look at this. Example of property. Okay, let me start. The example of property 3, I would like to skip now. About the look, the nomenclature sometimes instead of that they use this nomenclature here, no? But yeah, just to notice, not in all books they write that. It's in a scalar, no? It's an operator associate which associates the matrix in a scalar, positive or negative. Could be also complex, not only real. Depends if you have a complex value in the matrices. Look at this. At this moment, forget the example of property numbers here, 7. Look at this. I have in a matrix 2 times 2 must be squared. What is the determinant of A? In accordance with the definition, and then we will see the definition a little bit later, is this multiplied this minus this multiplied this. Let me see if I have here the explanation. No, I will explain here. It is easy to remember. If I have a matrix 2 times 2, is the product between the diagonal matrix minus the product of the anti-diagonal. Excuse me, is the product of the diagonal elements minus the product of the anti-diagonal elements. That can relatively good have in mind. Huh? Let me explain this in accordance with the definition. Why so? And nevertheless, again, it's easy to remember. In the matrix 2 times 2, the determinant of A is the product of the diagonal elements minus the product of the not diagonal element or the anti-diagonal. And according to the definition, should also came from here, even though here it seems to be complex. But in any case, we have a sum between 1 and n. N is not written here. It should be better if I improve the definition, but I tell you, typically they don't put because yeah, somewhere before in books they write as n is the dimension of the matrix. This is enough to say that because you remember squared means number of row equal number of column. I don't know if I tell you or if it's written somewhere, probably yes. But anyway, if I didn't tell you, I tell you now. The matrix is square if the number of row equal the number of column. And this is n is the dimension of the matrix because it's enough one parameter, one element to say how large is this matrix. N equal 2, this means we have a matrix 2 times 2 because the number of column 2 equals the number of row 2. Otherwise, we cannot calculate the determinant. Now, the sum between 1 and 2, again, 2 is the order of the dimension of the matrix, square matrix. Look, please, minus 1 up to I plus j, which multiply ij, determinant of this. Oh, it seems to be in a contradiction. Seems to be in a contradiction because I use on the left the same operator on the right, but it's not exactly the same because here I am using the minor. I mean, if you consider exactly now the case 2 times 2, look what I have. I have j equal 1 until 1 means, I mean, until 2, but it's in a sum until 2. Huh? This means minus 1 up to what? Please pay attention. And fixed I. I fixed I. For instance, I again, if you look here, I is the row, characterize the row, J is a column. I mean, fixed I means in our case, for instance, I fixed the first row. For instance, I can fix also the second. Fix the first is easier. I fix I equal 1. This means -1 up to 1 plus 1, starting from 1. This means -1 up to 2. This means 1, which multiply. Please pay attention here. A11. What is A11? It's this element. Did you agree? Which multiply the determinant of the minor, which I have excluding I row and J column. This means I have to exclude this row and this column. Now, I told you very quickly this determinant, but the determinant of the scalar is the scalar itself. The determinant of the scalar is the scalar itself. Therefore, this definition is a little bit written very, very quickly when I have to define that's determinant of a scalar and the scalar itself and so on. But now we don't see the contradiction in our case because the determinant of a scalar is the scalar itself. Now I have A11 which multiply A22 because if the determinant of this minor is the determinant of A22, the determinant of A22 I have to define before. I didn't do because otherwise too heavy in the sense. I have this element here. I don't know if it's visible. Then I have to add what? Because in the sum, J equal 2. This means I is always equal 1. This means I have -1 up to 1 plus 2. This means -1 up to 3, which is -1, which multiply. Please pay attention now. A12, because 1 remains, is fixed. This means A12 is this, -1, which multiply A12, which multiply what? The determinant of the minor characterized by excluding this row I equal 1 and this column J equal 2. This means multiply A to 1. Ready? You don't have to calculate everything again with this at this moment. This is enough when we have 2 times 2 to remember that we have the product between, because it's in general, no? We calculate in general between the elements on the diagonal minus the element in the antidiagonal. Look at this. Determinant of 1, 2, 3, 4. 1 multiply 4 minus 2 multiply 3 minus 2. If I ask now in the exam, are the set of the row vectors depending or not? Dependent or independent? Or is the set of the vector of the in the columns depending or not? They're independent. If you look at the property which I told you before, the determinant not 0. But look, try to imagine. If I have here 1, 3, 2, 6. Try to imagine now what happens now. Again, try to think. 1, 3 as is, 2, 6. Dependent or not? Dependent. In fact, the determinant is 0. Why that? Because we have 1 multiply 6 minus 2 multiply 3, 6 minus 6. But they are depending. Please pay attention. 1, 3 and 2, 6 depending because it is enough to multiply the first column by 2 and we have the second one. They have the same direction. Remember, I told you about the same direction zone. But also the row vectors are depending. 1, 2, 3, 6. I don't know if it's visible. If we multiply the first row by 3, I have the second. We will see in the future that this table is also important because the dependence between row and column, they are connected. If the row vectors are depending, it's also depending of the columns. Interesting. And at this moment, I didn't tell you explicitly, but if you look at the properties, this means I can read the sentence 4 in terms of rows, and I can read the sentence 4 in terms of columns. This means also here implies what I am telling you now. I did an example, just an example. This means the sentence holds for rows, but also for columns. Okay. Now, let me show you this example here, and then we will introduce the new topic. I think for today it should be nice if we conclude this lecture, no? This until page 19. Look at this calculation here. It's quite general calculation, quite general. If you want, I can show you also a concrete calculation, but let me show you this. We can see that the idea is always to use the determinant of a matrix 2 times 2, because we have seen that the determinant of a matrix 2 times 2 is easy to be calculated. No? The product of the diagonal elements minus the product of the anti-diagonal elements. Look at this. The determinant of this table here can be seen in this form here. Why that? Look at the definition. The definition says sum. We have a sum. 3 elements. This block here, plus this block here, plus this block here. Why 3 elements? Because n equals 3. The dimension of the matrix is 3. I told you the dimension is the number of rows equals the number of columns. 3. 3 rows, 3 columns. Look. I fix the first row. I can fix whatever I want, but with the fix is easy to image. Please pay attention. There is also case in which it's suitable to fix different row. Which one? When we have a lot of 0 in the row. Why that? Because if you look at the definition, once I fix the row, the element of the row remain constant. This means if I'm in a row with a lot of zeros, it's suitable to fix this as a fixed row. Please pay attention. And fixed I. Here it's quite general. This means, let me consider the first one. We will see in some exercise looking for maximum minima that it could be useful to consider. I mean, if A11 and A21, A13 are 0, I need just to calculate this because here is 0, here is 0. This means I have to look through the matrix to identify in which row I have the maximum number of 0. And then I can fix this and I can apply the same definition. Let me go ahead. Now, fix the first one, A11, we multiply what? I will exclude the first row, the first row and the first column. It's determinant of this minor. We can do that. We have seen until now. Now, going ahead, I will fix this one. This point here, 1, 2, is in an odd position. This justifies this minus. I mean, it's -1 up to 1, 2. Here was plus because it was -1 up to 1 plus 1. I is 1. And I will increase I starting from 1 until 3. It's easy also to figure out the design. It's easy just considering the position of this index of this element here. Now this is extremely easy because it's symbolic. If I have an example, I don't know if I have it here. No. But now it's easy to see this. Here is quite similar. I have a -1 up to 1 plus 3. This is +1, which multiply 1, 3. 1, 3 is here, no? 1, 3. As before, we had the 1, 2. At the beginning, 1, 1. Multiply what now? The determinant excluding again the row 1, and now the column 3. This means this 4 element as minor. No? Determinant of this minor. The determinant of this minor. Let me see if I have an exercise. Be more concrete, but in any case, I think is and then we will open the last topic of today. One second, let me see. Ah. Look at this. We can see also in the next lecture what is the goal, huh? To verify if this is the function or somewhere we have a minimum and a maximum. Huh? Just to anticipate that is not something which is not applied. Look at this. Now we can calculate everything using the first row or the third row, because we have 2, 0 in the first row and 2, 0 in the third row. The second row is not so suitable. The calculation, believe me, we can demonstrate that I can fix whatever row, that the calculations, or let me say the value of the determinant is the same. I didn't tell you this property, but we can see also here if you like. But the second choice, choosing this second choice means if I choose the second row, is not suitable because the calculation is very long, very long, twice long. Look at the determinant, consider the first row. Look, I have just one element to be calculated. Because when I consider the element A or the H, it doesn't matter what, the first element A11 is 0, because I have to multiply A11 for something. A11 is 0, we can see, the first element is 0. Also, the element 13, first row, third column. This means I don't have to do anything. It's enough to calculate what happens for the position, let me say the position A12. This means -1 up to 1 plus 2. Because this -1 is the position 1, 2, I plus j. This means -1 up to 3, which multiplies A12, which is -1. You can see here. Why 2 times -1? Once is -1, which is fixed, up to 1 plus j. 1 plus j is equal to 3. -1 is there because the element A12 is -1, which multiply what? What remains, let me say, of the determinant of the minor, excluding the first row and the second column. This means, let me indicate also in zoom, The determinant of what? This multiply this plus this multiply this. Excuse me, minus. But in any case, it's 0. No? You remember, we have 4 elements. 1, 2, 3, 4. The determinant of these 4 elements. I think yeah. Remember, the determinant, I think it's okay to be explained. The determinant of these 4 elements, again, is this multiply this minus this multiply this. Remember, we have a C. It's minus 2. Look what happens if I choose this. Should be the same. Should be minus 2. We have, let me show, yeah. Let me consider now everything with respect to I equal 3. Let me write here. No? We have minus 1, which is fixed, up to what? This is the element 3, 3. This means 3 plus 3. I equal 3, j equal 3. Remember, here we had I equal 1, j equal 2. Therefore, 3. Did you agree? Which multiply what? The element. Now is 2. Aij. Aij is this here. 3, 3. 3 row, 3 column. Now, look at the determinant of the minor, excluding what? This row and this column. Remain these 4 elements. This, we have seen, multiply this minus this multiply this. This multiply this is 1 with minus is minus 1. Remember the rule for a determinant of 2 times 2, applying the definition, and then I told you, keep in mind, I don't know if you remember this. When we have in a matrix 2 times 2, we are able to calculate the determinant directly. The diagonal minus the anti-diagonal. This is minus 2 again. I don't know if it's visible. This is plus 1 multiply 2 multiply minus 1. Try to do at home this. If you fix I equal 2, you will obtain the same result, minus 2. I didn't tell you, but it's in a property, therefore fixed. But of course, we have to do 2 calculations, double of calculations. Now, if you have a matrix 2 times 2 is not, or 3 times 3 is not a problem, but in some cases, we have a matrix very large in some application. To save calculation is always in the value. Okay. Let me stop 3 minutes, 5 minutes, and then we will conclude. This half hour more or less with the new topic. Exactly. Eigenvalue or eigenvalues eigenvector or eigenvectors of a matrix. Let me here pause. Here, no, I think pause. Yeah. 5 minutes, I drink a water, and then I come back. Ich habe keine Glas hier. 5 minutes, so, das ist the last topic of today. Ne? Sowieso, theoretisch haben wir Zeit bis 4 vor. Ne?
Ja.
Ja, dann seid das schön. Wir können ja auch so ein bisschen sprechen über Dinge von letzte Woche, aber nur. Das wahrscheinlich ist neu. Ne?
Ja.
Kern, aber Eigenvalues ist bekannt.
Vom Namen her bin ich vielleicht irgendwas.
Ja, ja. Aber Kern, das wird die Sache jetzt. Ne? Okay, aber ist das natürlich eine Linie. Wie geht das auch?
ja, sich uns nur so orientieren. Das ist ein bisschen schade, weil wenn ich mir zeige, zum Beispiel meine Gruppe, habe ich schon gezeigt, weil wir ganz so gut, vielleicht kann man machen. Auch für die Leute von zu Hause. Wir machen verschiedene Themen bei mir, auch Wirtschaft. Haben ihr erzählt, was?
Dass ihr auch ein Kino Bett habt?
Ja, die Pippa habe ich nie gezeigt, das ne? Um das geht um solche Sachen, ne? So hauptsächlich. Let me see ganz schnell. Aber jetzt bin ich in Zoom, ich denke, erlaube mir ja nicht so raus. Okay, vielleicht am Ende der Vorlesung, ne? Äh, zu zeigen, was da ziehe danach, wenn ich zeige. Und zeige, dass mit diesen Kenntnissen, mit diesen Strukturen, äh, sind die Basen von anderen Strukturen, das erlaubt, Prädiktion in Wirtschaft, erlaubt, ja, ich werde ja zeigen, was. Mindestens keine Ahnung, sagen, der BEBA, aber allgemeine, der Titel von der BEBA, weil der BEBA sind voll von Gleichungen. So können wir so ein bisschen so zu verstehen, dass wichtig ist trotzdem diese. Und schade, dass solche Sachen hier haben eine Folgen oder eine Konsequenz nur in meine Komplementär. Weil andere Dozenten machen sie nicht so viele. Und das, wie gesagt, das ist. Okay, let me restart. Okay, let me now restart considering this definition, the definition of eigenvalue, eigenvector, or probably in some books you can find eigenvalues, eigenvectors. But let me start reading the definition. I have a matrix, a square matrix, very important. This means in this context here, the eigenvector, the eigenvalue, or the plural eigenvectors, eigenvalues are defined for square matrix. We define eigenvalue, let me say singular, of this matrix, the scalar lambda, if you consider the plural as in some books, eigenvalue of the matrix, the scalars lambdas. No, but let me consider singular. Such that A multiply V equals lambda V, where V is called eigenvector. This is the definition. Now, just a remark, we can see that if A in a square matrix with dimension n times n, or let me say with dimension n, in some books we say dimension n means n times n. Here we see the notation, A times n. Sometimes we omit also. V is its eigenvector. I forgot here. Eigenvector of a vector is all wrong. But if reflects this equation here is an eigenvector, n times 1. This means n row, 1 column. Otherwise, the product is not possible. Look now the rest of the remark or the rest of the slide. Starting from the definition, A multiply V, or the A dot V, A multiply V, equal lambda V, implies, please pay attention what I am doing here. A minus lambda E, everything is in the parentheses, multiply V equals 0. Why that? If you want, I can express better this. Let me this.
I don't know if this expression here is clear from here to here. It's probably not yet, no? Let me show you. Yeah, okay. Right, second. Let me copy the definition. The definition is something which I fixed, no? Now we will discover the meaning later, but again, I can define whatever I want. About the utility, about the meaning, we can discuss nevertheless. But let me go ahead without discussing. But nevertheless, let me tell you something, because could be useful. This is the definition. A little bit about the meaning of the definition. A multiply V equal lambda V. What does expression recall in your opinion? A dot V equals lambda V. Why this definition? Why this definition means, again, I can define whatever I want. But here, we can see something interesting in this possible definition. No? As the determinant, I try to intuitively to explain why this definition. Here it seems that this product here between the matrix n times n, this means what is the product here? The product is between the row vector of matrix A and this column vector. Remember, V is n times 1, times 1. This means in a column. We are speaking about one eigenvector, no? And one eigenvalue, because it's easy to proceed. It's easy to proceed. But in any case, for each eigenvector, we have this. This I can generalize in this form here. You can see A multiply V as a transformation of V through A. We will see this a little bit later during the semester, what is the meaning of this sentence here. We can see the transformation of V through A. I apply A to V. But what is this the particularity of the eigenvector? Does the direction of V remain after the transformation? Because if you remember, lambda is a scalar. If you come back to the definition, I will come back later, but lambda is a scalar. This means A transform V as a parallel to V. Do you remember the definition of parallel? No? Lambda is a scalar, positive, negative. It's interesting. This is the definition, the sense. Why it's important to define this structure. Structures, eigenvalue, eigenvector. Okay, let me explain the second part of the remark or the slide. Let me write something like that. Why I can write this sentence here? The reason is that because I don't know if this is understandable. If no, I can show you. The identity, identity matrix, no? N times N. I don't know if this is understandable for you. Identity matrix is the unit matrix. If you, it's not so, we cannot say so, but in order to understand. I don't know if I go, if I can go more in depth on this. If you agree with this, you agree also with this percentage. Should I go more in depth to show you this? Look. N element is a little bit boring, you know, believe me. Identity matrix. This is the identity matrix N times N. You remember, as I told you also during the last weeks, if I have to demonstrate in general the property of matrices or vectors, sometimes it's just boring because I have to consider in the general. This is the vector V. Do you remember I told you N times 1? N row, 1 column. This is 2, 1. This is, please pay attention, row, in accordance with the definition, row multiply column. Look here, row multiply column. I have everything 0 except the first element. This means V1, 1. Row multiply column. Everything is 0 except the diagonal element, which will take the second element. Now it's clear, if you continue, that we have exactly what I told you. Now it's a little bit more clear. Left equal right. This is the basic idea of all demonstration of properties, which I didn't do because it's boring. Also, this is boring, but once this is not so extremely boring, it's easy to see. Demonstration means left equals right. If I say that I V equals Z, in order to justify this. Now, once I justify this, look, did you like this? I copy again for you. Now, we are satisfied with the explanation of this. From here to here is easy. Did you like this? I think you like. I can subtract this element on the right. I can subtract the same element on the left. I have this. Clear. From here to here, I think I don't need to explain. Then I put in evidence, please pay attention, on the right. From here to here, I don't know if from here to here is clear what I did. I put in evidence, please pay attention, on the right. Or on the left, this element here, it depends. But let me write V will multiply everything on the right. Multiply on the right, on the left is different between vector and matrices. Anyway, I think it's intuitive from here to here. Otherwise, I can again do more explicit, but I don't think so. We need now. Now, please pay attention. This expression here says something more. It nevertheless says the definition, because I manipulated just the definition. I mean, I obtained this expression just manipulating the definition. This means I can define eigenvalue and eigenvector, and eigenvalue as an eigenvector, also in this form here. Did you agree? I did just a trivial consideration, this here, at the beginning. And then from here to here, I just, let me say, moving on the left, and from here to here, just algebraic consideration. I didn't, this means this expression here is equivalent to the definition. But say something more, and let me conclude with the slide, and then we'll discuss again through the slide the definition, considering now does V, the eigenvector, is something, we say, that belongs to the null or kernel of this matrix. Meaning, you remember at the beginning I told you that A multiply V, or that A applied to V. If I apply this matrices, we will see during the semester this matrix in a transformation. But forget at this moment this. We have as a result, this product as a result is in a vector. The product of A multiply V is in a vector as a result. The matrix multiply in a vector, the result of a matrix multiplies is again in a vector. But if this vector V is in a particular vector, is an eigenvector, we transform, or the result of A multiply V is again in the direction of V, because lambda is in a scalar. We can see the scalar lambda. The scalar lambda. But in any case, to calculate V and lambda, I have to really consider this expression here, because here in this definition, I have two elements and just one equation. I have a V, I have a lambda, but just one condition. But now I can characterize better lambda and V. For instance, V is an element. If I write the definition in this form here, we can see here directly, the definition can be written in this form here. It's something which belongs to the null of kernel of this matrix here. What is the kernel of a matrix? What is the null of a matrix? Isn't it elements, let me say, we will see a little bit later what is the kernel, what is the null, probably also here. I have an exercise. No? We will see a little bit also using the exercise, but the kernel is let me say today a direction. Let me say is in a set in general which annihilate the matrices. This means the matrix which I have multiply an element which belongs to the kernel is equal to 0. This means the kernel is a set of elements and a vector. The kernel of the matrix M is A minus lambda E in our case, multiply V. If V is in the kernel in this set, which annihilates the product, this means M multiply V equals 0. At this moment, we will see, I will be more precise later. No? But now, I don't know if you remember the interesting property of the determinant. Look here, before speaking about why this expression. Of course, please pay attention. V equals 0. V equals 0 satisfies this condition here. let me consider A minus lambda E equal M in a matrix. M multiply V equals 0 for each V equals 0 is satisfied. This means 0 is always an eigenvector because satisfy this. But we don't consider V as an eigenvector because the trivial solution, I mean, V equals 0 is an eigenvector for each lambda. This means, okay, this does not characterize the matrix because each matrix its transformation, we will see matrix and transformation, is characterized by the vector or eigenvector equals 0 because 0 is transformed into 0 for each lambda. This means we have to exclude this. Otherwise, the definition includes this, but we are not interested in this because this is trivial. It's clear that we belong to the set of eigenvectors is an eigenvector, but it's the trivial one. Everything multiplied by 0 is equal to 0. Why we are here today in the evening? We don't need to be here. Therefore, excluding this, please pay attention. It is an important consideration. Excluding V equals 0. But what is the meaning of excluding V equals 0? The meaning is when this linear, please think about the matrix M. Here we have a matrix M. When M equal multiply V equals 0 as in a system, admits not trivial solution. I come back 1 second to this long list of property of the determinant. We are looking for something, V, which is not 0, because 0, we don't need to be here. Everything is clear. Multiply by 0 is equal to 0, it's satisfied. The definition must say something more. The definition is an effort to understand how I can define. And then it's trivial. Why have I to define? I mean, I can define, but I would like to exclude this. When this is important for us, when V is not 0. Look what I told you. (11 and 12). Look at the 12. If its determinant is not 0, we have only 0 solution. If the determinant is 0, we don't have only 0 solution. We can read also in the form. Let me see if I can. But also from here, no? Because if I have a linear system, we can have only 0 solution. In this case, we have this result, but we cannot have only 0 solution. And this means the determinant must be 0. In our case is M. M is A minus lambda E. It's a dichotomic situation. No? Only 0 solution or not only 0 solution. With only 0 solution, the determinant is equal to 0. Not equal to 0. If the determinant is equal to 0, we don't have only 0 solution. It's just dichotomic. No? Therefore, this is the condition. If the determinant is equal to 0, we don't have only 0 solution. Now, thanks to these considerations, thanks to the property of the determinant, we can calculate at the beginning lambda, and then using lambda directly from the definition, we can apply the definition, we can calculate V. This means the definition is constructive because we have, yes, apparently one condition. But in this condition, thanks to the property of the determinant, we have two, we can see this condition in two subconditions. Please pay attention, the matrix M is A minus lambda E. Basically, M is parameterized by lambda. Let me do the exercise, and then we will come back on this. Let me do something easy. Yeah, let me do the second exercise. The first exercise is easy, but is the same, but with more calculations. Let me do the second exercise, which can be easy to be understood because we have less calculations. It's the same. The idea is the same. The application is basically the same, but here, yeah, the calculation is easier. Look, matrix A equals 1, 2, 0, 4, right? Exam. Please calculate the eigenvalues and eigenvectors. All eigenvalues and all eigenvectors. I didn't put properties, but I can tell you that a matrix n, order n, or the dimension n, at n eigenvalues and n eigenvectors. We have also some properties depending, independent eigenvectors. We will see probably a little bit later. In order to speed up, we have also properties and so on. I didn't tell you about that. But in a matrix with dimension 2, admit two eigenvalues, two eigenvectors, could be same eigenvalues, multiplicity eigenvalues, and then implies some characteristic in the eigenvectors. But in any case, the number of eigenvalue eigenvectors equals the number of the order of the matrix. But let me do the exercise. It's easy to do the exercise than to explain. Calculate eigenvalues, eigenvectors. Look, we learned that to calculate the eigenvalues, we have to calculate determinant of A minus lambda E equals 0, because this is the condition which guarantees not only 0 eigenvector, or better to say, we calculate the not 0 eigenvector. The 0 eigenvector we don't need to calculate, it's there. Each 0 vector is transformed into 0. Look, apply the definition, determinant of what? 1, 2, 0, 4 minus lambda, which multiply I is the identity matrix. 1, 0, 0, 1. You want to equals 3. From this expression to this expression is easy. 1 minus lambda, 2 minus 0. I think we don't need to explain this. I mean, the difference between, here I have to multiply lambda by the matrix. This means I have to multiply lambda everywhere. Because do you remember the scalar which multiply the matrix means the scalar which multiply each column or each row of the matrix. Therefore, you can see here lambda multiply this matrix equals lambda 0, 0 lambda. Then the difference between two matrices is the difference, I told you very quickly, but it's intuitive, is the difference of each corresponding elements. This means it's intuitive to say that the result is 1 minus lambda, first element, 2, and then in the second row, 0, 4 minus lambda. If this is not clear, I will explain with the lateral camera, but it's intuitive. I have to subtract each element. Before subtracting, I have to multiply this scalar and this matrix. But this means to multiply each column or each row by lambda. Now, please pay attention. The determinant of this, we know, because it's this element, or the diagonal elements, the product of the diagonal elements, minus the product of a non-diagonal element. This means y minus lambda, which multiply 4 minus lambda, we can see here, minus 2 multiply 0. I didn't put 2 multiply 0, because it's 0. I don't know if it's clear. This element multiply this element minus 2 multiply 0. At the end, I have this expression. Now, we can understand very well the concept of the matrix M, which I did input here, is parameterized by lambda. I can calculate for which lambda the determinant of A minus lambda E is equal 0. Lambda 1 equal 1, and lambda 2 equal 4. This is 0 for lambda 1 equal 1 and lambda 2 equal 4. Two values for lambda. This means from the definition, what is the meaning? For the definition, we calculated for which lambda 1 and lambda 2, we have eigenvectors not 0. We don't have the eigenvectors, not yet, but we have the lambda. And then we can see here in this slide, to lambda 1, we will correspond in V1. For lambda 1, we will correspond in V2. Now we can directly apply the definition. Look, the last slide. Now, you can apply this, which it is the definition, or you can start with the original equation as you want. As I say, because we obtained this expression here, starting from the, let me say, original definition. Look, 1204 A minus 1001. Why that? Because lambda equal 1. We are calculating V1 in this case. Now we can see at the end of these calculations, V1, we correspond to lambda 1 equal 1, which multiply AB. What is AB? AB is the parameterization of the eigenvector V1. I can write two general parameters, A and B, which characterize the vector V1. V1 is AB as the vector. This is difficult a little bit. This is written very quickly, but here is, you can see here V1 characterized by two parameters, A and B, equals 0, 0. This element here, this 0 here, please pay attention, is in a vector. This 0 here is in a vector, n row, 1 column. This means 2 row, 1 column is here. Because the vector V1 is characterized by 2 row and 1 column, which I don't know where is. Which element are, excuse me. Now, this difference is easy, 0, 2, 0, 3. Because 1 minus 1 is 0, 2 minus 0 is 2, 0 minus 0 is 0, 4 minus 1 is 3. I have to subtract the corresponding elements, which multiply AB. Look, must be equal 0, must be equal 0, no? In accordance with the definition. Row multiply column. 0 multiply A plus 2 multiply B. We can see here. 2B equals 0, because I have to satisfy the principle, the equality principle. No? This is in a vector. The result of this product is in a vector. This vector must be equal to this one. The first element of this vector is 2B. The second element is 3B. I don't know if it's visible. 2B equals 0, 3B equals 0. When these two conditions are satisfied, necessarily B equals 0. But very important for each A, because A is not involved in the conditions. This means what I can say from these two conditions, B must be 0, A for each, because it's not involved. It's satisfied for each A. This means V1 is 1, 0, multiply the parameter A. I don't know if this way to write is understandable. If A could be everything, is A0 the vector? Or the direction, if you don't like to say the vector? This is the eigenvector. For each A, we say 1, 0 is the eigenvector. Huh? Look, the second calculation. Here is similar, but instead of lambda 1, I have a lambda 2. Lambda 2 was 4. This means instead of 1, 0, 0, 1, I have a 4, 0, 0, 4, right? Lambda 2 was 4. Here I have a 4 which multiply the identity matrix. 4 which multiply 1, 0, 0, 1. I have this. Which multiply the eigenvector V2, which I characterized by two different parameters, C and D. If I do the same calculations before, look, I will obtain minus 3, 2, 0, 0. Subtracting this matrix to this one is easy to see. I don't know if it's visible, no? Minus 3, 2, 0, 0 from here. Then again, row multiply column, I have now, please pay attention, minus 3C plus 2D equals 0 from the first condition. And from the second condition, extremely interesting, because I have 0 equals 0. This means this I am totally satisfied directly. I don't have to add any conditions. Now, from this condition here, I have that, for instance, D equals 3C divided 2. Or if you don't like, C equals 2D divided 3. You can choose whatever you want. But we have a condition. But this means, if I write in this form here, D equals 3 divided 2C, and for each C, because C is not involved in conditions. This means V2 is 1, 3 divided 2, everything multiplies C. We can see that C appears in both components, the first and the second, because D is the function of C. We'll go in depth next week. If I have questions, I am here to answer questions. Otherwise, of course, we can close here because it's the time. Yeah. Let me stop the. Why does it work?